All right, guys, today we're gonna finish up with our very last day of integrating new things. After today, you will be able to integrate everything that we will learn how to integrate in this course. You know, in future courses, there are some other techniques that can be used, but for our course, today is the last day. We're gonna start with something a little tricky, which is a warm-up. And what makes today's tricky, I think. But what makes this a little bit tricky isn't that any one problem is hard, is that it's hard to know which technique to use. You kind of have to go through in your heads, you know, which one is appropriate. So try these three warm-up problems and see if you can figure out how to do the integral. The first one, I noticed that the denominator is x cubed and the numerator is x squared. And so I'm going to say that the denominator is x cubed is going to be u. And the numerator is going to be du, because the derivative of x cubed plus 5 is 3x squared. So when I notice that the derivative of the denominator is up in the numerator, or even something that's the same degree, it could be off by a constant multiple, that tells me this is going to be u substitution. So this is, sometimes it's helpful to rewrite this as 1 over x cubed plus 5 times 3x squared. And so we can really see this is 1 over u, that was my u, times du, times the derivative of u. And the integral of 1 over u is the natural log of the absolute value of u plus c. And so let's substitute back in the u. U is x cubed plus 5. So we get natural log of the absolute value of x cubed plus 5 plus c. And that is our antiderivative. If you were to do the derivative, it would be, the derivative of natural log would be 1 over this times the derivative of the inside, which is where the 3x squared comes from. Okay, here's the second one. Don't get too stuck in a certain place in your head. This time, the denominator, the derivative of the denominator is not the numerator. If we were to say u is x squared, then the du would be 2x, which would not cancel out the numerator. And you never want to like say the numerator is the u, unless it's like a natural log or something weird, because you can't divide by du. Like even if this was exactly right, which it's not, it still wouldn't cancel this out. But even if it would, you can't cancel out the denominator. You always want to look for the u in the denominator and the du in the numerator. So what can we do here? This is not u substitution. Well, remember one of our previous techniques was you can always just simplify something first. So we can divide everything by x squared. X cubed divided by x squared is x. 5x divided by x squared is, one of the x's cancels out, and we get 5 over x. So we've got this integral. Oh, I should have put a dx on all of these. dx, dx, dx. Man, I did that throughout this. I'll go back and edit this before you guys have it. So the integral of x is 1/2 x squared. And the integral of 5 over x, this is another natural log one, is 5 natural log absolute value of x plus c. So here is our integral. And the last one is, so real quick, on this previous one, the reason we could divide this one by x squared is because there was only one thing in the denominator. And when there's only one thing, you can split it up. So it's this divided by this and this divided by this. So that's nice. And the last one is a slightly different one because there's not one thing in the denominator. Let's check and see if it's u substitution. If u is x squared plus 1, you're always checking the denominator to see if it's u. Then the du would be 2x, but 3 divided by 2x will still have x's in it, and so it doesn't cancel out the x's, right? So u substitution won't work because the degree of the du isn't the same as the degree of the numerator. So this isn't u substitution. You can't split it up, so what can we do here? Well, hopefully we recognize that this is 3 times 1 over x squared plus 1, and this is another integral you're supposed to know. This is arctangent, so tangent inverse of x plus c. So I think this is tricky because, you know, there's 3 different techniques, right? There's u substitution, you've got divide everything if there's a common single denominator, and arc trig functions. Like sometimes even if it's like square root of x squared minus 1, like, or 1 minus x squared, sorry. You know, like this also looks like maybe it's going to be a u substitution. And if there was a 2x on top, then it would be. But if there's not a 2x on top, then it's arc sine, right? So there's two different techniques we have to look for. Now, we're going to look at two different techniques today. The first is, and I actually want to slow into this a little bit. First is, what if we have 1 over 9x squared plus 1, okay? Now, and we want to do the integral, okay? Well, the first thing to think about is, which one of these? Is this u substitution? Well, the derivative of the denominator has an x in it, and there's no x in the numerator, so it's not u substitution. There's not just one thing in the denominator, so you can't split it up. It looks kind of like our arctangent, except for this 9 in front. And so when this one is 1, and this one is something x squared, you can do an arctangent using a u substitution. What we're going to do is we're going to change this to 1 over u squared plus 1. And so we have to think, what is the square root of this? And that will be u. So u will be 3x. And the reason this will be 3x is because 3x squared will be 9x squared. So this can be rewritten as u squared. Okay. Now, du here is 3. The derivative of 3x is 3. And so we'll always have to divide by the du. Now, there's no number on top here, so I'm just going to bring the 1/3 to the outside. 1/3 integral of u squared plus 1. And this is du. And so now I can actually do this. This is 1/3 arctangent, or I could put tangent inverse of -1 of u plus c. So 1/3, I'm going to put tangent inverse just so we can see both ways, and u was 3x plus c. And you kind of see, right? Like, this will work when you do the derivative of it. The c will go away. The derivative of tangent inverse is 1 over x squared, this squared, plus 1, and times the derivative of the inside. The 3 will multiply times the 1/3 and cancel it out. So we can do this using u substitution. Now, our example in our notes is even more broad. It turns out that if you have, something like this, you always want to check, is it u substitution? Well, the derivative of the denominator has an x in it. The numerator doesn't have an x, so it's not u substitution. There's two things, so it's not splitting it up. If there's just a quadratic plus a number, you always can do this using u substitution. And the way it works is you first take whatever number is here, and we need to turn this into a 1. This we can mess around with u, but this we need to become a 1. So what we're going to do is we're going to factor out of the integral whatever this number is. So we're going to factor out 1/2. The denominator, we're not doing anything with that. The numerator, we're factoring out the 1/2. And so now this is 4x squared plus 1, and I want you guys to try to finish this on your own based on what we did just a minute ago in our other example. Hopefully, you saw that u here should be 2x, and then du would be 1/2. Or sorry, du would be 2. We're going to divide by 2, and it's going to factor out 1/2. So this is the integral of 1 over u squared plus 1, and we need to divide by 2. I'm going to bring that to the outside. 1/2 divided by 2 is 1/4, and this hopefully is where you got to. This is du, and now I can do this integral. This is 1/4 tangent inverse, or arctangent, of u plus c, and u was 2x, so 1/4 tangent inverse of 2x plus c. So I hope we see how this works. So here's a new technique. So we had these old techniques before. Okay, u substitution we look for. If there's a single thing in the denominator, we can split it up. And if there's an arctangent, we can do it. But now we can actually get arctangent ones using u substitution. Okay, so let's practice this on another one and see if you can do it all the way on your own. Hopefully that went well for you. And now let's look at a new one. This one, okay, so let's look for u substitution. The derivative is 2x plus 8. That's not in the numerator, okay? Let's look, we can't split it up because there's 3 things in the denominator. If there's only 1 thing in the denominator, we can split it up. So this one is also an arctangent one in disguise because we can complete the square. We can turn it into a squared function. So what I'm going to do is I'm going to complete, let's take our algebra 2 skills of completing the square. So we want to turn this into a square binomial. And I'm gonna put the plus 17 out here. Remember from Algebra 2, we bully out the 17, we make room to make a square binomial. Then we figure out what square binomial this is gonna be. So when you square a binomial, you square the first one. So that'll give us x squared. Then these two multiply together and double to make 8x. And so this needs to be plus 4. So x plus 4 squared will give me x squared plus 8x. And the last term is 4 squared. This will be 16. This needs to be plus 16 to make it a square binomial. And if we add 16, we have to subtract 16 to cancel it out. And so we get plus 1. And so this is 1 over x plus 4 squared plus 1. Now look, guys. Now this looks like an arctangent. Except we need to do a u substitution. What is our u here? Our u is going to be whatever the squared term is, x plus 4. And so du is 1. The derivative of x is 1. And so we don't really need to divide because dividing by 1 doesn't do anything. So this is the integral of 1 over u squared plus 1. And so we're going to get, I'm just going to go ahead and substitute back in the arc, the u at the end. Tangent inverse of x plus 4 plus c. So I hope we can see this was tangent inverse of u, and I just put back in u as x plus 4 into there. So if you see a quadratic in the denominator, it's worth thinking about, can you complete the square to make it into an arctangent function? You know, one of the cool things, I started to mention this in last class's video, but I got cut off, is if this came up in the multiple choice, you could actually just like do the derivative of each of the answer choices and see which one gives you the antiderivative. You know, like this is saying what's the antiderivative? Well, you just do the derivative of all the answer choices and that could tell you what's the right answer. All right, this last one. It looks like an arctangent, but there's this thing on top. It's not just 1. You can have any constant on top, because basically you can factor out a constant outside of the integral. You can't factor out an expression or a function outside of the integral unless it's a constant. That comes back to our properties of integrals. You can't divide the denominator. Let's see, is the derivative of the denominator the numerator? No. The derivative would be 2x. That would not cancel out the x squared. And so we need a new technique. Our last technique is going to be if the degree of the numerator is bigger than the degree of the denominator, you can do long division. It's kind of what we did here where we divided each of these by x squared, but as long as the degree of the numerator is bigger, you can do x squared even if there's more than one term by doing long division. So we're going to say 3x squared plus 5. I guess we should say plus 0x plus 5 is getting divided by x squared plus 1. So we need to leave space here. So x squared goes into 3x squared how many times? That's 3. 3 multiplies times x squared plus 1. And we need to line it up. So 3x squared, 3 times 1 is 3. That goes over here. So the 0x's didn't actually matter there. But sometimes it does. So 3x squared minus 3x squared is 0. 0x is a 0. 5 minus 3 is 2. And that's the remainder. So the 2 is still getting divided by x squared plus 1. So this is the integral of 3 plus 2 over x squared plus 1. And we can do the integral of 3 and 2 over x squared plus 1 separately. Why don't you guys try it from here? Hopefully you notice that the integral of 3 is just 3x, and that this one, okay, the derivative of 2x still isn't in the numerator, but it's a quadratic, and this is an arctangent. This is going to be, you can factor out the 2 to make it 2 times 1 over x squared plus 1. This is going to be 2 arctangent of x plus c. So we can use long division to rewrite it as multiple terms that we can do individually, and that makes it easy. So let's see. I hope I gave you a chance to try this one, and I want to give you a chance to try one of these real quick. So practice this on your own. And then the question is, how do we tell which ones to do? If there is only one term in the denominator, like this, split it up. Right? So if there's only one term in the denominator, split it up. And an example would be like x to the 5th plus 2 over x cubed. If we want to do this integral, there's only one thing in the denominator. And there could even be more things in the numerator, right? Like, okay, cool. But let's see. When we split it up, x to the 5th divided by x cubed is x squared. We haven't done the integral yet, so this integral symbol should still be here. We're just rewriting it. Plus 2 over x cubed, I'm going to write this as 2x to the negative 3 power, because I know I'm going to have to do power rule on this in a second. If it was 2 over x cubed, that's not natural log. Natural log is only when it's 2 over x. So sometimes these end up being natural log ones, but if it's a different power other than x to the negative 1, then it's just power rule. So now we can do it. 1/3 x cubed. This will raise by 1 and divide by the new power. So 2 divided by negative 2 is negative 1 plus c. So 1 over 3x cubed minus 1 over x squared plus c. So we can see how we can find the antiderivative by splitting it up. Hopefully we feel okay about that. If the degree of the numerator is greater than or equal to the degree of the denominator, if it's at least as big as the degree of the denominator, we can use long division. If there's only one thing in the denominator, you want to split it up first. That's better. But we can do long division. So if the numerator has a bigger degree, which means the power of x is higher, then we can do long division. So, you know what's funny is I don't actually have a good one prepared, and I'm worried I would like mess it up. So I'm not gonna. I'll give you a chance to practice another one of these in a second, but I'm not gonna make one up right now because it's actually kind of hard to come up with. Okay, the numerator is a constant. If the numerator is a constant and the denominator is quadratic, then we can use arctangent, right? Sometimes with u substitution. So let me see if I can come up with an example on this. So the integral of 5 over x squared plus 6x plus 10 seems like a good example to me. So let's see. Now I see 3 things here. So this is going to be the completing the square kind. I'm going to factor out the 5 to the outside. So 5 integral of 1 over, I need this to be a square thing. So x squared plus 6x plus something. I'm going to bully out the 10. So this is going to be x plus something squared, x plus 3 squared, because 3 times x is 3x. 3x doubled is 6x. And so this needed to be a plus 9 up here. So if it's plus 9, we have to do minus 9. And so we get, this is x plus 3 squared plus 1 dx. And we can use u substitution here. Here, u is x plus 3. When du is 1, you can kind of just like ignore the chain rule and just do it in a way. This is just 5 arctangent of x plus 3. Plus c. Because the derivative of x plus 3 is just 1, so you don't have to like divide by the u or anything. You can just see that this is like 1 over u squared plus 1. Or you could do, I mean, like if you said u equals x plus 3 and did 1 over u squared plus 1 and substituted back, it'll get you the right answer also. So the last thing is, what if the numerator is the derivative of the denominator? So an example would be like 5x. So the integral of 5x over 3x squared plus 1. The derivative of 3x squared is 6x. Oh, sorry, I should have said this is u substitution. So if the derivative, and it can be off by a constant multiple, it just needs to be the same degree. So 6x and 5x, those will end up canceling out. So when I divide by 6x, right, this is the integral of, I'm going to rewrite this as 1 over 3x squared plus 1 times 5x. And when I divide by 6x, that will cancel out the x's, and I'll be left with just a constant. So this is the integral of 1 over u, and I'm going to put the 5, 6 out here, du. So, you know, the u substitution definitely is going to come up a lot. This is 5, 6, natural log, absolute value of u plus c. Hopefully you're feeling okay about these. Now, guys, let's do some mixed practice. I think each one of these techniques by itself isn't that bad, but figuring out which one to do can be really tricky and take some practice. So hopefully by the time we've gotten our practice today, I think once you've practiced today and practiced your homework, you will be in great shape to be able to do this. By the way, guys, u substitution comes up like, I don't know, 5 times on the AP exam. U substitution is gonna come up a lot. These other techniques will come up like once or twice on the AP exam combined. So, you know, if you're struggling a little bit with the natural log, with the arctangent stuff or the long division stuff, those don't come up nearly as often as use substitution. But you do want to be able to tell like which things you can do use substitution on and which you can't. So this first one, which technique should you use? And hopefully you see there's only one thing in the denominator. So we should divide everything by x squared. This is the integral of 3, because 3x squared divided by x squared is just 3. Here, one of the x's will cancel out, so we get 6 over x. And here, nothing cancels out, and we get 1 over x squared. Since x isn't just a power of 1 there, I'm going to write x to the negative 2 power. Now we can actually do this integral, just do them separately. The integral of 3 is 3x. The integral of 6 over x, this one, when there's just a single x there, that's natural log. This is 6 natural log, absolute value of x. This one is going to be power rule because it's not just over x, it's over x squared. So this is 1 over x squared, and so that's going to be a power rule one. So x to the negative 1 power, we need to divide by the negative 1. I wish I hadn't written this plus here, plus c. So 3x plus 6 ln of x minus 1 over x plus c. This next one, which technique are we going to use? Well, hopefully we see that the denominator is a quadratic and the numerator is a constant. So this is going to be one of those. Arctangent ones. And in this case, we need to divide by the 9. We need to factor out the 9 to make this, but this is now going to be 1/9 x squared. I guess I should factor out the 6 too. Why not, to make that a 1? So 1/9 x squared plus 1. We had to make this a 1, but when you factor out the 9, it's going to divide this one by 9 also. And so what is this? Well, we're going to have to use u substitution. U is, what is the square root of this? It's 1/3 x. So du is 1/3. So this is going to be the integral of, I guess I should rewrite this. This was 2/3. 6/9 is 2/3. This is the integral of 1 over u squared plus 1 du. To undo the multiplying by 1/3, we have to divide by 1/3. Dividing by 1/3 is the same as multiplying times 3. So we're going to multiply by 3 here to undo the multiplying by 1/3 that the chain rule is going to have here. And those 3's are actually going to cancel out. That's really nice. So we're going to get 2 arctangent or tangent inverse of u plus c. And this is 2 times tangent inverse of u is 1/3 x plus c. So tricky stuff, guys. How about this one? Well, okay, so there's not a single thing. There is a quadratic, but it's not a constant in the numerator. This looks like maybe it'll be a u substitution. Let's check. If u is x squared plus 5x, the derivative is 2x plus 5, and there that is in the numerator. So this is the integral of 1 over x squared plus 5x times 2x plus 5. This is the integral of 1 over u du. Great, guys, we can just do it. This is a u substitution. This is natural log absolute value of u plus c. So natural log absolute value of x squared plus 5x plus c. Okay, how about this one? Okay, well, this is a weird thing in the denominator. It doesn't look like it's an arctangent. The degree of the numerator is smaller. Boy, this looks like u substitution. What would the u be? Well, the numerator is an x squared, so I know I need an x cubed in the denominator, and that looks good. So x cubed plus 1 is u, so du is 3x squared, and that'll cancel out the x squared here. So this is the integral of 1 over u squared, and x squared divided by 3x squared is 1/3. So when we do x squared divided by 3x squared, the x squareds cancel out and there's still a 1/3 left over. So hopefully we feel okay about that. I'm going to move this. Okay. So this is power rule. This is u to the negative 2 power. We're going to raise the power by 1 and divide by the power. So negative 1/3 plus c. And so the answer is negative 1 over 3 times 1 plus x cubed. Yikes. Tricky. Okay. How about this one? It looks a lot like an arctangent at first. Like maybe I can divide by 9. It looks a whole lot like this one up above. But there's no constant in the numerator. The derivative of the denominator is 2x. That won't cancel out with an x squared because it has a different degree. The degree of the numerator is as big as the degree of the denominator. And so I can't split this up because there's not just one thing in the denominator. If this had been x squared plus 9 over x squared, I could just divide everything by x squared, but you can't do that when there's more than one thing in the denominator. But I can do long division. I can say x squared is getting divided by x squared plus 9. X squared goes in one time, and so 1 times x squared plus 9. When I subtract, I will get 0, which is good. 0 minus 9 is negative 9. So minus 9 over x squared plus 9. So this is the integral of 1 minus 9 over x squared plus 9. Now, I can do the integral of this. This is going to be x. But what about the integral of this one? Well, that's the same kind as up here. It's now a constant over x squared plus 9. My goodness, we're going to have to do more than one technique. So I'm going to split this up into two integrals. I'm going to factor out the 9 here. And I also need to factor out a 9 from the denominator to make this equal to 1. So I guess I'm going to factor out 9 over 9. I'm going to factor out the 9 from the top. That'll be just a 1 here. I don't know why I put the integral here. This is a 1 on top. I factor out the 9. And when I factor out the 9 from the bottom, it divides this one by 9 also. So 1/9 x squared plus 1. We always have to make this one equal to 1, remember? This one always has to be equal to 1. And so now this is an arctangent with u is equal to the square root of this. This is 1/3 of x. So du is 1/3. The integral, so this is, I'm going to leave this as the integral. I'm not going to do it yet. This was 1 integral of 1 over u squared plus 1 du. And to cancel out the du, I have to divide by 1/3. That is multiplying by 3. So I'm going to multiply by 3 on the outside. So x minus 3 arctangent of 1/3 x plus c. My goodness, that was tough. Okay, this is harder than I would guess any of the questions on the AP exam are going to be, but maybe not. I mean, there could be one that hard. It would just be like on the really hard end. They always try to have like a couple that like even most people getting 5s are going to miss. How about this one? Okay, hopefully we notice there's a quadratic on the bottom with a constant on the top, so this is going to be arctangent. So we need to make this into a square binomial. So this is going to be x squared plus 10x plus something. So we need to actually do this. So what square binomial will this be? Well, this is x plus, we divide this one by 2. That's the fast way to do it. So we just divide it by 2 because these will multiply together and double to make 10x. And so let's go back up and actually complete the square. So x squared plus 10x is plus, this is going to be 5 squared, which is 25. So we subtract, this was 26. We subtract 25 and we get 1. Okay, great. So we get the integral. I'm going to factor out the 3 to the outside of 1 over x plus 5 squared plus 1. And we can see that u is x plus 5, so du will just be 1. So we don't need to like divide by 1. This is just going to be 3 arctangent of x plus 5 plus c. And if you did use substitution here and said like u equals x plus 5, great. That's fine. How about this one? Let's see. There's actually 2 ways to do this. This is cool. I could do this as a u substitution because the derivative of cosine of x, so if u is cosine of x, the derivative is negative sine of x. And so I can divide by that and that'll cancel out the numerator. So let's do that. When I'm doing u substitution, I really like to rewrite this as 1 over cosine of x, cosine squared of x times 3 sine of x. So we can see what'll happen when I divide by the du. So this is 1 over, cosine is u, so 1 over u squared. And when we divide by negative sine of x, the sine of x's will cancel. So I'll divide by negative sine of x. This will be negative 3, and I'm going to just bring that to the outside. We could leave it inside the integral, it's cool, but I like factoring out the constants to the outside. So negative 3, this is u to the negative 2 power. This is power rule, so it's going to be u to the -1 power and divide by a -1. So that's going to be 3u to the -1, which is 3 over u, which is, I guess I should put plus c. So 3 over cosine of x. Now, we could do that using u substitution, but there's a much older, we've done this problem before, I believe. There's an older way we could do it, which is with trig functions. You can look for like special things that you notice, like sine over cosine is tangent. So this is 3 tangent of x, and so that's sine of x over cosine of x. Now that was only one cosine. This is cosine squared, so there has to be another cosine of x here. That'll make cosine squared. And so this is tangent of x, and 1 over cosine of x is secant of x. So this is the integral of 3 tangent of x secant of x, and we should recognize that this is the derivative of secant of x. Tangent of x secant of x is the derivative of secant, so this is just 3 secant of x plus c. And boy, that got us the same answer. Secant of x is 1 over cosine of x, so it's the same thing, but if you recognize that you can do, like, rewrite it as a trig thing, that saved us a lot of time and not having to do u substitution, so that's nice. How about here? Let's see. I can see that there is a quadratic in the denominator, but the derivative of, like, this isn't +1, so it's not going to be an arctangent. Instead, u is going to be x minus 1 because the derivative of u is just 1, and that's in the top. Or it's like there's just a constant in the top. So this is just integral of 1 over u squared du. We need to raise the power by 1. Sorry, this is u to the -2, I guess we should say. Du. So we're going to raise the power by 1 and divide by the new power. So negative u to the -1. And so we have -1 over u plus c. -1 over x minus 1 plus c. There is our u substitution. Okay, guys, 1 over cosine squared. My first thought is the derivative of this in the numerator, so like if u is cosine of x, the derivative would be sine of x, negative sine of x, but there's no sine of x in the numerator. So this actually is not one of the techniques we've been talking about today. Instead, this is one of the trig ones we should already know. Let's rewrite this. 1 over cosine of x is secant of x. And so this is the integral of secant squared of x. And the integral of secant squared is just, what's the antiderivative? What thing gives you a derivative of secant squared? Well, hopefully we know that's tangent. Tangent of x plus c. Done. It's one of those trig ones where you have to know the derivative of the trig function. Okay, and here, oh my goodness, this one's hard. Here, this is a weird one. When, like, natural log should set off alarm bells in your head because sometimes it ends up being the u. So if u is natural log of x, then du is 1 over x, and this is 1 over x. So I'm going to rewrite this as natural log of x squared times 1 over x. So here is my u, here is my du. So this is the integral of u squared du, right? So the natural log of x is the only time you're looking to see if the denominator is part of the du is if there's a natural log, because the derivative of natural log is 1 over x, and so sometimes you can end up with the derivative of the numerator giving you the denominator. Usually we only care, like, the denominator could be the only thing that's u, but if there's a natural log of x, that could also be the u. So the integral of u squared is 1/3 u cubed. We raise the power by 1, divide by 3, plus c. So this is 1/3 u was natural log of x. 1/3 natural log of x cubed plus c. Okay, guys. The first thing I would look for is the derivative of, like, is this the inside function? The derivative of this would be negative 2x, but there's no negative 2x on top, so it's not u substitution. This is one of our arc trig functions. This is 5 times 1 over square root of 1 minus x squared, and this we're supposed to recognize as sine inverse. And that's it. It's just like you have to know this derivative. Oh my goodness, even more hard stuff. Okay, here I notice that there is and x cubed plus x in the bottom, so it doesn't really look like anything. The derivative of the denominator is 3x squared, but that's not in the numerator. So what can we do here? It doesn't look like any of our techniques work, but I can simplify this. You might notice there's an x in all of them. So this is the integral of, I'm going to divide everything by x. I'm going to divide by x over x. So 5 over x squared plus 1. And now I can see that this is an arctangent because it's x squared plus 1 with a constant on top. So this is 5 arctangent of x plus c. So these three bottom ones didn't really fit with our rules for today, but it's a good reminder that like you still need to know other rules too. I think this was a really tricky lesson just because, and it just takes practice until you get used to it, guys. Like once you've done it, a few of these situations a few different times, you'll start getting used to it and it'll get easier and easier and easier. Practice, practice, practice is the trick. Once you get enough practice, like these things, like the techniques of what you look for and what process you go through to look for it will get easier and easier. I hope you guys have a good rest of your day. Make sure you practice your homework on this stuff to get to the place where you feel pretty good about it. Have a good rest of your day.